See, can you hear me through one of these? It's working. Good. Good. Maybe so we don't get feedback. If I were younger, I could see how to turn that off. But, oh well. So we need a quantum time machine so we can become younger. Certainly I do. So my name is Robert. My given name is Robert Ewald, and I'm an American. And so, of course, Americans have nicknames. And Robert has 6 letters, and then as a young Robert, you become Bobby, which has 5 letters. And then after a while, my friends called me Big E. As I got bigger, my friends called me Big E, which had 4 letters. And then you become Bob, which had 3 letters. And I worked at Los Alamos about 10 years, and for a story that is much longer than we have time for, they started calling me Bo, which has 2 letters. And soon I'll just be B, and then off the air. So on average, I'm getting about 12 years per letter. And we're hoping that, in fact, with D-Wave computing, we can move through our generations much more rapidly than that. So thank you very much for visiting with us this morning. We're very pleased to be here. I kind of grew up in high-performance computing and graphics, computer graphics. I did some early work on computer graphics. Amongst other things, I did special effects for the first Star Trek movie that was many, many years ago. I was at Los Alamos for about 10 years and ended up running the computing division there. And it is because of the Los Alamos connection that we're able to be here today. Our friend Bart, wherever he went, in the back, is on a postdoc at Los Alamos National Lab in the U.S. And so we met him through Denny, who you'll hear in a minute, and Bart invited us to come today, so originally invited us. So thank you very much for having us here. I then spent the next 10 or 15 years at Cray Research, where I was the president of the supercomputer company, and then was CEO of a company called Silicon Graphics, or SGI, and have done other things. So I've been at D-Wave about 3 years, and it is, of all of the great things and places where I've worked, it is the one that is the most exciting, the most revolutionary, the hardest to use, the most challenging today, but will have, I believe, the biggest impact on the future of computing of all of the things that I have been able to work on. And what we have today with the D-Wave machines is really a physics machine on which you can compute, as opposed to a computer on which you can simulate physics. It's kind of the other way around, in a sense, compared to the way we have historically done computing. So I will talk a little bit of background about what led to the formation of this company, introduce some of the background papers that led to it. And then Andy Mason will talk a little bit about the hardware. We'll introduce you to the hardware. And then Denny Dahl will show you how the software works. And if our internet connection holds, we'll be able to run some live quantum computing programs on live machines in North America. So that's... That will be the format for today, and we're informal, so if you have questions, feel free to ask as we go along. So of all of the great companies and places that I've had the opportunity to work, this is the first computer company that I have ever known that was on the cover of popular magazines. For many of you, you don't know what a magazine is, but they're printed on paper. They used to be mailed to your house, and you would turn them page by page. They're not electronic. This was a popular old American public magazine, or a popular magazine called Time Magazine. And about 2 years ago, D-Wave was featured on the cover of this magazine, and you can read, and it was called the Infinity Machine. And you can read in yellow the subheadings, which sort of encapsulate part of what it is, or the theory, or the folklore, perhaps, about D-Wave. And I don't know that we promise to solve some of humanity's most complex problems, but certainly some of the most challenging scientific and engineering problems that exist. We expect to be able to help with those. And Jeff Bezos, the founder of Amazon, is an investor in our company. NASA is not an investor, but Google was our second customer, and they operate NASA Ames in Silicon Valley, operates the Google machine. CIA is not an investor in the company, nor do they own one of our computers that I know about, and I would know that. However, the investment arm of the intelligence community in the US is called In-Q-Tel, and they have invested some money in D-Wave. Each one, the machines actually cost $15 million. Time said they cost $10 million. That's sort of become the street price of our machines then, because it was on the cover of Time. And the point to that is it's a supercomputer class machine. And it does operate at near absolute zero. About 15 millikelvin is what where the temperature that the chip operates. And nobody knows how it actually works is at least partially true. It is a very complicated, new, unique device, and we understand lots about parts of it, and other parts we're learning more about. So this is a company that had this idea, built this computer without having all of the theory understood behind it, so it's more an empirical approach to it. Let's build something, see how it works, and then we can adjust things and try it as the theory sort of catches up here. So the idea for quantum computing, of course, goes back to, well, ideas go back a long, long way, or parts of the ideas, but Richard Feynman in 1982 started postulating that, in fact, you would be able to build a quantum computer. I can't quite do his hands, but it's something like that. And the first time I met him and saw him talk about it was in 1983 when I was at Los Alamos, and it was the 40th anniversary of the laboratory. And it is hard to read, but he was the speaker who came on at 9 o'clock that day to talk about his early ideas about how one might be able to build a quantum computer. So that's sort of where the ideas about organizing electronic devices to be able to build a quantum computer got started. And basically what we are trying to do is, rather than fighting against quantum effects as we have done in traditional computing for 50 years, we're trying to harness those quantum effects. So in traditional computing, a quantum effect could cause a bit to flip from a 1 to a 0. Well, we try to take advantage of that, rather than not the flipping, but the quantum effects behind that. So rather than fighting against quantum effects, we try to take advantage of it. Or quantum tunneling is another one that you historically fight. So we try to use quantum effects to our advantage. And in the digital computing world that we come from, it's a binary world, or we want it to be a binary world. We've made it be a binary world, really. So a bit, an individual piece of information, is either a 0 or it's a 1, nowhere in between. That's well known. We use that principle. Those bits or words in a computer are all separable. And then lastly, if we hit a barrier, whether it be on a transistor or if we're doing a search and we're trying to find the low spot, say in a landscape, we have to put more energy into the system. More energy at the transistor, or if we're doing a search, we have to do more computing to climb a mountain and look over the side to see if there might be a lower valley on the other side. And in our quantum world, what we're doing is using the principle of superposition, and we'll talk more about that in a minute, but we use superposition where a bit is a 0 or a 1 and both simultaneously. So we'll come back and talk about that. Secondly, we use entanglement, and this picture doesn't have anything to do with anything, but the idea of entanglement is rather that in the digital world, where if my fingers were each a bit, those 10 bits are separable and independent. If we can cause those bits to become entangled, then we can no longer treat them as 10 independent bits. Rather, we have to think about them as a unit. And then lastly, and perhaps the easiest one to visualize, is quantum tunneling, where now if we hit a barrier, rather than having to put more energy in to climb over the barrier and at least look down or go to the other side, we use quantum tunneling to go through the barrier. And the ideas then, beyond Feynman and postulating that you could build a computer using those quantum effects, in 1984, a man named David Deutsch in the UK proposed a way to start organizing how one might build a computer in a way sort of like John von Neumann did in the late 40s and 50s about how to organize what became a traditional computer. And that then led to a series of theoretical algorithms being developed for a theoretical quantum computer. And that theoretical quantum computer is what we today call a gate model or a universal quantum computer. Doesn't exist at any scale yet. There are experimental devices, and IBM has recently put a 5-qubit machine. IBM Research has put a 5-qubit machine on the web that you can start trying. But this led the idea of a quantum computer then led people to say, well, if we had one, these are some of the things that you could do with it. And probably the most famous of the algorithms is Peter Shor's algorithm from 1994. And it's postulated that if one had a fully functional universal quantum computer and you could run his algorithm, you would be able to break all previous codes that had been encrypted. Now, to our knowledge, there's no one that does that yet. No one can do that with our machine. Our machine does not run Shor's algorithm yet, so it's probably a long way until that happens. But that's the one that you read about, and people are either very afraid of or they can't wait until that could happen. So theoretical algorithms, it's estimated that there are about 1.5 billion euros a year being spent on quantum computing research of one kind or another around the world. A lot of that money is going into research on devices, a little bit on software, a lot on quantum communications of one kind or another, and then a fair amount now on quantum computing. And we're going to focus on the right side of this picture, which is the quantum computing side. We talked about the gate model, or some people call it the universal model of quantum computing. Realistically, that's where IBM and others are headed with their machines. In the long term, we believe our machine will become more universal, but that's what they're talking about. In IBM's announcement of their 5-qubit machine, they said it's probably at least 10 years, perhaps 20 years away before such a thing could be commercialized. So, and we hear that from others. We were this week at the International Supercomputing Conference, and I was talking to a person from Intel who said, yes, they're just starting to look at a universal or a gate model machine. And he said, rather than measuring projects in the quantum world in years, they're measured in decades. So he said the people who were starting their research there said, well, it'll be 1 decade or 2 decades or maybe 3 decades before we have a machine. So those are probably quite a bit away. Microsoft and others are looking at a different approach called topological. We'll spend the rest of the time talking about the one thing that you can really implement at scale today, which is the Adiabatic model. And again, we'll show you what the hardware looks like and then how you program it. And it is quite different. But the ideas for this type of computing, annealing, some people call it, quantum annealing, go back actually to, this is a paper from the early 1950s by Nick Metropolis, who was then at Los Alamos, and the Tellers, and also the Rosenbluths. And they came up with an idea for how to use traditional computers in what they called, what became called simulated annealing, where basically you would do a part of a calculation, you would sort of harden it or stop, you would anneal it, then you would change the boundary, relax the conditions, do a little more computing, harden it again, and continue that. So over time, that idea that went back to the early 1950s became called simulated annealing. And then in about 1998, some researchers at Tokyo Institute of Technology postulated that you could take that idea and perhaps build a quantum computer around it. And in fact, I was in Japan about 1 month ago, and Nishimori-san, who is the second author here, as well as his student Katawaki-san, hosted us at a meeting in Tokyo, and we had 200 people attend. And again, they're part of the heritage here of creating this type of computer. And then some people at MIT and elsewhere further refined that idea. And then as it happened, at about the same time, there were 2 PhD physics graduate students at the University of British Columbia. And they had just taken a course on entrepreneurship. Those are popular courses in North America. Basically, how do you become rich in a short period of time? And so they took this course and said, well, let's start a business. What do we know about? Well, we know things about things, we know physics, some, and they were very confident. And we know about physics, and we know about things quantum, and those are going to be important in the future. And so the first thing they did was start collecting patents, creating and collecting patents around things quantum. And then, at the same time, these other ideas that from MIT and Japan and some from Europe were coming along, and they said, maybe we could actually build a quantum computer. And they met some people who had been working on superconducting devices from TRW and Northrop Grumman in the US, and those people said, we could probably build superconducting devices that perhaps you could use as quantum bits or qubits. So the ideas, the architectural ideas came from academia, the drivers came from these 2 people with ideas, and then fortunately, they met these device people who said, we think we could actually build something. And then they started hiring more engineers and engineering physicists, and that led to the first of these quantum machines. So the company is one of the longest running startup companies ever. It's in its 17th year now. We have about 150 employees. The company has raised over $150 million US, which is a lot of money, long running startup. And the first customer of a 128 qubit machine was Lockheed Martin. Lockheed Martin bought a 128 qubit machine about 5 years ago, and then about 3 years ago upgraded it to 500 qubits, and then about 6 months ago we upgraded it to 1,000 qubits. The Lockheed Martin machine you may see on the web sometimes. It's housed by the Information Sciences Institute of the University of Southern California. And so if you have research with ISI, you can get some time on that machine. So Lockheed bought the machine, University of Southern California operates it for them, and it's about half available to Lockheed and about half available to USC and its affiliates. The second customer was Google. And Google, we'll show you why they bought it, but machine learning is their primary application at Google. And so Google bought the machine, said, we think it has some application in machine learning, but we're going to ask our neighbors, the NASA Ames Research Center, which is a big supercomputing center, to run the machine for us. So Google bought the machine, housed at their neighbor NASA Ames, and again, Google has about half the machine, and researchers in the NASA community have the other half. And then our third customer became Los Alamos National Laboratory. They bought this machine in last September and wanted to start running on it immediately, so they started running on the machine in our factory, and we're right now in the process of installing it at Los Alamos. In fact, I'm going to beat Bart and Denny back to Los Alamos. I'll be there on Monday, and we have meetings, but we'll be taking pictures of the installation of this first-of-a-kind machine within one of the Department of Energy laboratories. So it's it's a fascinating state-of-the-art business with 3 customers so far. So what we're looking for are places who have their own applications, who have a lot of smart people, and who believe that quantum computing will be part of the future, and that it's time to get started today. Because it's a little challenging to use here, and it is like the 1950s, I think, in traditional computing. This computer is quite different than anything you've seen before, certainly than I've seen before, and it's maybe more analog. More like an analog computer is the way to think about it. This is my simple way of thinking about it. If you could imagine, or if you could create a problem that is, in this case, a 3-dimensional landscape of mountains and valleys, What this computer does about 10,000 times a second is it finds the lowest valley or valleys in that landscape. Probably. So it's probabilistic. We don't guarantee that it's the lowest valley or valleys. That's a little dependent on what the problem's like. And it's not really a three-dimensional physical landscape. It's an n-dimensional energy landscape. And what we're really doing is finding the lowest energy state, probably. So what you do with this machine is, rather than get the answer, you'll give it a problem and you'll say, run this problem 100 times or 1,000 times, and you'll get a distribution of answers come back. And if your problem has, instead of very low mountains and the valleys are all the same, if it has very high narrow mountains and there's a very low valley somewhere in the landscape, most of the answers will be in that low valley. But if it's more like a piece of sandpaper, so a flat piece of paper with little grains of sand glued to it, then where there's no clear low valley and where the mountains are not really mountains but just little hills, then you'll get quite a wide distribution of answers. So different than traditional computing, where the answers you get back are dependent on the problem you ask it to solve, or the distribution of answers are. But this is the simple way to think about what it's doing, is landscapes, finding the lowest valley or valleys in that landscape. And that sounds a lot like an optimization problem. And so we believe that we can help solve some challenging combinatorial discrete optimization problems, and we'll talk a little bit more about those. Google and others have shown us that you could apply this landscape solver to machine learning problems. And then it looks like you can also use it for sampling or Monte Carlo sorts of applications as well. Different than anything we've ever bumped into before. So I went to the Intel manuals, and the middle column is a list of some of the characteristics of a 64-bit Intel architecture machine, where performance for most scientific computing is measured in flops, floating point operations per second, and we're up to bazillions of floating point operations per second. We do 0 floating point operations. This machine natively couldn't add a number if its life depended on it. That's not what it does. 64-bit precision, we have with today's machine about 5 bits of precision. So when you specify this energy landscape, you don't have too much dimensional latitude, if you will, to specify it. That we'll work on that as we go along. Instead of doing billions of instructions per second, we do about 10,000 instructions per second. But each instruction causes this causes a solution of this energy landscape to be sought. So it's quite a different concept there. Instead of 500 instructions, as at the machine language or assembly language level on Intel, we have 1 instruction. So those of you who are computer scientists, this is a really, really, really reduced instruction set computer. It's very easy. It's very easy to learn that 1 instruction. We'll show you what it looks like. The little challenge is in mapping your problem onto that 1 instruction. That's where the creativity comes about. It operates at near absolute zero. I think the coldest place that astronomers have measured in the universe is a galaxy far, far away somewhere that's at 1 or 2 Kelvin. And we're running at 15 millikelvin in a complete vacuum with no vibration, no radio frequency interference. Quantum computing is a little delicate, so we have to make sure that our chip is in a specialized environment. And maturity here at the bottom, I should say about power consumption, the device, the computer, if that's what we should call it, is superconducting. It uses virtually no power. But the entire system uses about 25 kilowatts. Most of that goes for the network interface computers to allow you to get on it and then to monitor it and to run the cooling equipment. So we use pulse tube dilution refrigerators, as those in physics are probably familiar with. But we've gotten them so they run for months and months and months at a time. So quite different. Before Google bought their first D-Wave machine, they said, let's create some benchmarks and see if it could perform. So they created a set. So this is about 3 and 4 years ago now when these charts were first created. And they created a set of random discrete combinatorial optimization problems that they wanted to run. There were about 500 of these benchmarks that they gave us. And this is a timing chart, so lower down the chart is better. And what this chart shows is how long it took to solve these benchmark problems as a function of the size of the problem. For us, that was measured in qubits, from 1 qubit up to 500. And what you would see, maybe 2 things to point out. The D-Wave is the red line, and the blue and green and purple colors are off-the-shelf optimization software. C-Plex is from IBM. MaxStat is another package, and Taboo is a third optimization package. So they wanted to compare what you could do with the D-Wave to off-the-shelf software running on, in this case, it was an Intel server. And what you see is that small problem sizes, the D-Wave machine is 100 times slower than the traditional approaches. It crosses over, and when we got out to about 500 qubits, the D-Wave machine was a little over 10,000 times faster than the commercial traditional approaches. Would also point out that the red line, the D-Wave line, in the real world, we're used to, as the problem gets bigger, it takes more and more time to solve the problem. That's what the blue and green and purple lines are. That's what we're familiar with. The D-Wave machine does about 10,000 solutions a second, no matter the size of the problem. It takes us a little longer to load it at 500 qubits than it did at 2 qubits, and that accounts for the little difference that you see there. But reality is, again, no matter the problem size, we do about 10,000 of these solutions a second. So that's why the D-Wave line is essentially flat. So Google said, wow, we don't know if we can map our problems onto it, but if we could, it looks like the performance, there is some performance that we could get out of that machine compared to classical. And then what they next did is said, let's work together and see if we can train this machine to be a machine learning engine. And so we set about doing that with them. And this now took another 6 months to do. And they gave us a set of 500 or so training images, many of which had cars and many of which didn't, and some had elephants and rhinoceroses and trees and things. And after 6 months of work, we were able to figure out how to train the D-Wave machine to recognize cars. And on their traditional machines, they were about, with the algorithms at that time, they were about 84% effective at recognizing cars correctly in that set of images. And the D-Wave machine was about 94% effective. But more importantly for that, when they took the classifiers from the D-Wave machine that were used to recognize a car, put them back on the traditional machine, that the traditional machine only used about 1/3 of the CPU cycles to get a better result. And the project that was driving this at the time was Google Glass, which is a battery-operated computer. And if you can save 2/3 of the CPU cycles on a battery-operated computer, you've saved 2/3 of the battery life. So that was a huge win for Google, or potential win. So they said, it looks like if we're clever, maybe we can get good performance out of the machine, and it looks like with a lot of hard work, we can map our application onto it. So let's buy one. So they did. And they have since then upgraded from 500 qubits to 1,000 qubits. And then they also have signed a 7-year contract with us. And we have 6 years left of that contract now, where every 2 years or so we will upgrade the Google machine to the state of the art. So it showed us that they have some confidence in what we're doing and where we're going. And then more recently from Google, and we can give you copies of these slides if you would like, but this was Google and NASA had a press conference on December 8th of last year, so 6 or 7 months ago. And at that, Google said now they understand how to use the 1,000 qubit machine better. And their first benchmarks were these random optimization problems, but they said now we think we understand it better, and we're going to create a benchmark which has very steep, very narrow mountains, and then has a very low valley. And let's solve that on the D-Wave machine. And then compare that to simulated annealing and quantum Monte Carlo. And that's the result that was 100 million times faster on the D-Wave machine than on a single core, in this case, Intel machine running simulated annealing or quantum Monte Carlo. So 100 million that's a pretty big number. And so again, that I think gave them more confidence that there is a future here, but it is challenging to map things onto this machine. So good progress in just 3 years, and more to come, because we've been on a path where about every 18 to 24 months we've been able to double the number of qubits on our machines. And where we installed the first 1,000 qubit machine 1 year ago at Google. And so let's see, 24 months from there would be about a year from now. So I would expect by a year from now we'll be fielding 2,000 qubit machines roughly. So very rapid pace, great developments, challenging environments like nothing that I've ever encountered before. It has more potential, however, in the future, I think, to change the face of computing than any of the other great companies that I had a chance to work at. So with that, if would be, and we'll be here, I think, most of the day today, and some of us will be around part of the day tomorrow as well. Would next turn it over to my colleague, Andy Mason. Andy looks after our business across Europe. Andy is actually an electronic engineer by education and training, worked in the communications world for quite a while, then moved to Cray Research a few years, Cray Computer at the time. I was Cray Research, he was Cray Computer. And then we were fortunate to have Andy join us about 2 years ago. So, and Andy will talk about